Okay, good morning. Can you guys hear me okay? Cool. Hope you are doing well. So, as usual, let's start with announcements. So I'll jump to that. First, someone pointed out that there was an issue, or seemed to be an issue, with question 3 on day 25. Namely, it was not accepting what would have been a correct input for, I think, the last part of question 3. And it affected some people, but not everyone. A few of you may have noticed that your score jumped up a little bit, and that's because I went through and I saw that some people had the correct thing, but it was not being accepted. So I did some score adjustments there. And if you feel that you did enter the right part into the right solution in the last part of day 25 on that question 3, let me know and I'll go back over and look over. I tried to get everyone's score adjusted, but I may have missed some. But that was that. So there may have been a score adjustment there you noticed. And then I want to talk about this upcoming week because there's a lot of review in this upcoming week. And again, that's by design. I intended the first 2 weeks to be the most difficult, and then for us to kind of keep repeating the material over and over in review to try to reinforce it. And hopefully the course gets a little bit easier as we go on. So next week, on Monday, we'll look at linearizing systems, which is just a follow up to what we'll talk about today. So today we'll talk about linear systems. And then on Monday, we'll talk about linearizing systems. So we'll look at how to solve linear systems, namely using Laplace today. And then we'll look at, how do we get them to be linear if they aren't linear to start with? If they're not a linear system initially. But then after that, Tuesday, Wednesday, Thursday next week is going to be all review. Tuesday will be review of first order topics. Then Wednesday will be a review of higher order topics and so on. There'll be a review video, as it has been before, for each. Well, I mean, there currently is a first order review video. There is a higher order review video. And then I'll post a Laplace review video. In addition to the video you can watch on higher order topics on Wednesday or before, whenever, we'll also have a Zoom meeting where we'll also go over these topics. And then exam 3, like before, is comprehensive. It's got a good chunk of each one of these areas: first order, higher order, and Laplace. And from the comments you guys gave me last time, it seemed like a number of people actually liked that it was comprehensive, so you could build on what you've already seen. And indeed, that's the case here for exam 3. There will be, I'm looking at it right now, 10 questions, but some of them are very, very quick. Like one of the questions you can answer in a few seconds. So it's really going to be, I think, about the same, what should I say, the same time commitment maybe as the last one. Of course, that's a big caveat. That's what it seems like to me, and it varies per student and so on. But like I said, a few of the questions you can answer very quickly, and so I don't think it's going to be a ton longer. And then someone's asking, when will the reviews be open? That's a good question. I intend for them to be kind of open whenever. I'll look here really quick. I thought I had opened them by that Monday of next week, but I'm not 100% sure I did. So let me look right now. And if not, I will open them by Monday unless you guys feel you want them even earlier than that. Yeah, okay. Now I need to change these dates. I'll remind myself of that. So note to self. Change review availability. So maybe you guys can give me your feedback. Is Monday of next week having the reviews open by then? Is that early enough, or would you prefer it open over the weekend to work on it? What would your preferences be? So reviews, these 3, daily homework reviews, open this weekend, or is Monday fine? What would you prefer? I want to balance having them kind of close enough to the exam that you're more fresh, but also early enough to give you more time to reflect and so on. So I see 5 comments so far, and 4 are for the weekend. So I will change it to the weekend. And of course, you can always wait until later if you want to have it work on it closer to the exam. So change review availability for the weekend. Okay. I will. And if I don't remember to do that, if you don't see it like available as of tomorrow, just let me know and I'll make sure to get it done. Okay, with that, so thanks for your feedback if you provided that. Now let's go ahead and open it up to questions that you have. Today's topic, I think, will not be incredibly difficult. In fact, I think it'll be relatively straightforward, I think. So, given that, there is lots of time for questions, I think, if you have any. So, first question right out of the gate, swinging hard is, what is convolution? Yeah, good question. The answer immediately is, I actually don't know offhand. I was kind of wondering that myself as I was reviewing. I know, the mathematical definition, but as far as the physicality of it, I'm not totally sure if it represents something uh, like a physical phenomenon or what. But yeah, I'm not sure offhand. I would kind of like to know it. Not sure if it's a mathematical, quote unquote, a mathematical trick. That is, someone set this up because they thought it would be mathematically useful for solving equations, or does it represent some physical phenomenon? Actually, I'd kind of like to know, so maybe I'll look after class here. Yeah, but the long and short is I'm really not sure, but I'll try to find out and get back to you guys. Next question. Uh, could we do written homework 5.1b? Okay, let's take a look at that. Written homework 5.1b. I'll bring that up here. Okay, so using the initial conditions, x naught or x of 0 is equal to 2 and y of 0 is equal to 1/2, determine the parameter in your implicit solution from part A. That's 5.1b. All right, if I remember, I think I walked through this with someone. If we've got, and let me maybe put this on another page. So 5.1 written homework, we have dx dt is equal to 4x minus 2xy. And then we have dy dt is equal to xy minus 3y. So first I need to do part A, or run through part A really quick. We can represent dy dx as dy dt over dx dt. So just to get us set up here, and that would look like xy minus 3y all over 4x minus 2xy. Then we will get what we can factor out of y, leaving us with x minus 3. And then we can factor out an x, leaving us with 4 minus 2y. And that's going to be separable. We can write it as 4 minus 2y over y dy is equal to x minus 3 over x dx. Now, once we go through this process of doing the integrating, so we've separated the variables, now let's integrate. And I think we're going to get ln of y. There's a little bit of algebra to do to simplify, but just to get to it. And then minus 2y is equal to x minus 3 ln x. Again, do a little bit of algebraic simplification and then do the integrating. And one way we can write this is ln y to the fourth using log properties plus ln x cubed. Again, I'm going through this maybe somewhat quickly or jumping some steps just for the sake of getting to part B. This is all part A. And we have x plus 2y. If I seem to miss something, let me know. But then we can combine those and get ln y to the fourth x cubed is equal to x plus 2y plus c. And the long story short is we're going to end up with y to the fourth x cubed is equal to e to the c, which you could relabel as c1 if you like, ex plus 2y. Now from here, we can substitute in the initial data. So all this was just part A. I'm going to move this to a new page just to clear away some of the work we've done here, just so we can focus on what's important for the moment. So we end up with this. And then what we're given for part B is we're told x of 0 is equal to 2, y of 0 is equal to 1/2. And what we want to do is find the parameter. So the parameter in question is just this thing here, which you could write as e to the c, or just call it c1 if you like, as long as it's not c again, but maybe c1 or d or whatever you want to call it. And at this point, all you're doing is you're substituting in. Now, you don't actually substitute in 0, because what you're saying in effect here is this is the same as y of t to the fourth, x of t to the third is equal to c1. And this is e to the x of t plus 2y of t. So we've suppressed the notation here. But if you substitute t is equal to 0, x will be 2 and y will be 1/2. So when t is equal to 0, that is, you have y of 0 to the fourth, you have x of 0 to the third is equal to c1, e to the x of 0 plus 2y of 0. Now you can substitute in 2 and 1/2 appropriately for all these, and then you'll be able to solve for c1 from there. All right, that is that part. So that's part B. C, since someone also asked about C, let's follow that up. So written homework, part C. So again, there's just a little bit of work left to do with the B from what we did here. And then C, on the other hand. So what we're trying to do is find equilibrium points where these are both 0. So what you want is these to be simultaneously 0. That would be an equilibrium point. And if you try to find that, let's say we just look at this first equation. So this first equation gives us that 4x should be equal to 2xy. Now you have either one of two possibilities. You could have that x is equal to 0, or you could have that, actually let me kind of highlight it more. You could have that x is equal to 0, Or you could have alternatively that x is not equal to 0. If x is not equal to 0, you can divide by it, and that gives you 4 is equal to 2y, or y is equal to 2. And then in each of those cases, you can check this equation. It should also be equal to 0. In one of the cases, substitute in x is equal to 0, find y. In the other case, substitute in y is equal to 2 and find x. And when I say substitute, I mean substitute into this. So again, I won't finish that one off completely, so I don't just do the whole thing, but that should get you going on that problem. And just to highlight, there's two equilibrium points. One is found on this path and the other is found on this path. Someone asked about question 3 on the online homework from yesterday. Yeah, so to the person who asked about question 3 from online homework yesterday, you may have been here. I did mention that there was an issue in the code with that, and a lot of people had the correct answer, but it just wasn't being accepted. So I did make some adjustments to the scores there, but let me go back to it. And so, yeah, actually, if you asked about going over that question 3, was it because you thought you got it right and it wasn't accepting it? Or was it because you weren't really sure how to do it? What were your thoughts on that? Okay, so let's go ahead and look at it. So this is question 3. All right, question 3 from the homework. Let's go ahead and look at that from the day 24. All right, so what was going on with this one? What we had is f of t. This is a good one to go over anyways. Even if you saw how to do it, it's good for the practice. We have f of t is the Heaviside function shifted by 7. G of t is t squared. This should be the same. Well, the only thing that would be different for different people is what this is, this minus 7. You might have minus 9 or something like that. But this will work out largely the same. If we want to compute the convolution, just by definition, this is going to be the integral from 0 to t. And now what we do is we have f. Maybe I'll color that like this. And then g. First we take f. We have u of t minus, and they use tau. So maybe I'll kind of put it in bold here to highlight it. I used a previously. You can use whatever you want to make it easy to tell t apart, but we'll use this here. And then we have something squared. And that something should be t minus, again, tau. And that's d tau. I'm trying to, hopefully that tau looks bold, because that's what we're going to actually be doing the integration with respect to. All right, now at this point, what we want to use is the fact that u of t minus tau is going to be 0. Wait a minute. That's not t minus tau, it's tau minus 7. There we go. So any instance of t in the first case, we replace with tau. So t gets replaced with tau. And then in the second case, we take any instance of t and we replace that instance with not tau, but t minus tau. So there's two different substitutions to make. The first function, t gets changed to tau, and in the second case, t gets changed to t minus tau. So here we switch from t to tau, and then here we switch from t to t minus tau. Now, with the Heaviside function, that function, if we were to graph it in just like a little mini graph, what that is 0 up until you are at 7, and then you jump up to 1. But the important thing is that you are 0 up until 7. So for all the values 0 to 7, this integral is going to be 0 times this, which is just integrating 0. Therefore, we can change this function to be like this, where we go 7 to t. And now we've let this be 0. So that meant we could change this lower limit of integration. And then from there, it's just going to be 1 times this. So once we hit 7 after that, we're just multiplying by 1 here. So what we get in the end, in that case, is t minus tau. That gets squared, and then we have d tau. And I should say the 7 came from the Heaviside function. Now, at this point, it may help just for a second to imagine that we have something similar to this, because we have, t and tau, and it can be confusing. If we had, let's say, 4 minus x squared, and we wanted to find the antiderivative of that with respect to x. That's a notation we're a little more familiar with. What this will amount to is 4 minus x cubed, and then times negative 1/3, plus your c. Now, how did I come up with that? Well, one way you could come up with it is just through u substitution. So u substitution, technique we saw, I think, Calc 2. That, in this case, we would let u be equal to 4 minus x. Take the derivative, du. It's going to be negative dx. So dx is negative du. Then once you do that substitution, what you will have is the integral of negative u squared du. And it'll work just the same here. We've made some substitutions just to kind of change the notation and make it a little more familiar, but it works out identically. I'm going to move this up a little bit. So when we take the antiderivative, what we'll get is what? We'll get, maybe I'll switch to green now, or actually, let's do yellow. We'll get negative 1/3. T is just a constant because we're integrating with respect to tau. So just treat it like the 4. So we get negative 1/3 t, just a constant, minus tau. And then that's going to be cubed. But then we are going to evaluate it from t is equal to, or not t, tau is equal to 7. Up to tau is equal to t. So keeping track of the tau and the t and what you're integrating with respect to, that's kind of the challenge here. And if you do this, I'm going to erase this work. Actually, I'll leave that. If you make this substitution, I'll just put it up here. If you make the substitution, what you'll get is negative 1/3 times t minus t, because tau gets substitute for t. That's t minus t cubed. And then we have minus a negative third, so we have plus 1/3. And then we have t minus 7 cubed. And in the end, of course, that amounts to just the latter part, this 1/3 t minus 7 cubed, where you may have had 9 or 6 or something like this, but it works out the same. You'll just replace that 7 with whatever you had. All right, so that's how you go through all of day 24, number 3. Hopefully that made some sense, but feel free to ask questions if there was a part I went through that I went through too fast or wasn't quite clear. Just let me know. And let's see. People are also asking about number 4 in the homework. And I'm going to assume that's the same one, the day 24 homework. Someone asked about number 4, and I'll assume it's this one. Oh, someone asked, where did I get 4 from? 4 in this problem, I just made it up. The reason there's nothing special about 4. I just wanted to choose a constant to work through an example so that you could maybe see that this 4, or maybe I choose 5 or negative 20 or whatever, it doesn't matter. But the point is it's a constant to try to line it up with this t here, where while we're doing this integration, since we're integrating with respect to tau, we treat the t as a constant because we're only taking changes in tau. We're not taking changes in t. So here, this would have been maybe a little more familiar because this is kind of the problems we first worked on when we learned U substitution. But you're still doing U substitution here. You're just letting U be t minus tau instead of let's say 4 minus x. And this, again, was just an example to help illustrate what you're doing here. So the 4, it's irrelevant. It could have been A, if you like. Doesn't matter. I could have just put A everywhere here. Would have worked out the same. Or for that matter, T. Could have put T minus X. Just as long as it's not X, that's the point. So 4 was arbitrary. I just picked something to have a number there. All right, so someone was asking about 4 and the graph. All right, if I'm looking at 4, a sample graph that I have, I'll show in a second. So day 24, this is number 4. I have a graph, for instance, that looks like this. Or, the one that just randomly generated when I pulled it up. It looks like it goes up to 1, jumps up for a bit, and then down here. Alrighty. And just to put some numbers in here, we've got 1, 2, 3, and then this height is at a height of 4. Also, again, if you can hear me like breathing into the mic or any annoying noises like that, let me know, because I would be super irritated if I heard this, and I'm paranoid that the mic is picking that up. So just let me know. I won't be offended. All right. If we take, let's say, the following thing like this, this would be like the graph, this graph would represent the following function. It would represent u of t minus 1. Now, the reason I'm bringing that up is because we're going to use that to generate the function to have this graph. If we take u of t minus 1, that's fine, we get this, but it's not quite this. One thing we notice is the height isn't right. Here's a height of 1. So if we change the height of this, or if we want to change the height, that might be the first adjustment we make. If we want it to be 4, let's say, so that it goes like this, that would be 4 times u of t minus 1. All right, so that gives the right height there. But then what we want is for it to also not just stay at 4 forever, but jump back down to 0. So what we need to do is essentially take away 4 at some point. But we only want to take away 4 starting at 3. So let's imagine another graph. That looks like this. Where what we do is we have a value of 4, but only once we get to 3, which might look something like this. And the idea is there that we're going to subtract these two. So if this hits it at 3 or jumps up at 3, this jumps up at 1. And let's say here for reference is 3. If you take the difference between these two, what you should get then is this thing here. So taking the difference of these two should, I claim, give you this. So you take and you say, start out with the 4 ut minus 1. That essentially gives you this part here to start with. And then it would keep going after that. But then what you're going to do is you're going to take and subtract the green function. Actually, let me finish this. You're going to subtract the green function, t minus 3. And if you do that, since that function looks like this, you can see maybe here what's going to happen. That if you take the difference, first take away, or first you have the magenta part, and then you have the green part. So taking the difference between magenta and green for 1 or less, t-value of 1 or less, you're taking 0 minus 0. When you're between 1 and 3, you're taking magenta, which is 4, and then you're taking green, which is 0. So you're taking 4 minus 0, so you have 4. Then once you get to 3, you're going to take magenta minus green, which is 4 minus 4, and that will give you 0. So just taking the difference, we see 0 minus 0, 4 minus 0, and then 4 minus 4. Someone asked, what does the U represent? I don't know. Yeah, I don't know where the notation came from. I think, you just had to pick something for it. I might have picked H, for heavy side, but maybe there was some other function that they didn't want to confuse with by having H be the notation for that too. I'm not sure why we use U for the heavy side. Good question. All right, with that, yeah, let's get into the topic. That was a lot of questions, which is good. Hopefully it was helpful to you, at least at some point. Now what we're going to look at is the following. We're going to look at linear systems. Until now, most of what we've been doing is taking a single differential equation and applying a method to solve it, or we analyze it in some ways. If it's a slope field, we could plot the slope field of a differential equation for some of them if they're first order, et cetera. And then we could analyze equilibrium points and look at typical solutions and so on. But a lot of it is just, okay, here's a diffie-q, maybe some initial value information. Let's apply a technique to solve it. The difference here is that we have more than one of them. And there's nothing saying you can have at most two. You could have three of them. You could have four of them. You could have any finite number of them. But just kind of starting at the next step up from one, let's go to two. We think of our variables x and y as both depending on t, let's say time. And if you think to this recent homework where we had the predator-prey model systems, you can think of it in the same way. Here's a population X that varies over time. Here's another population Y that varies over time. And the change in X depends on the relative populations of X and T. Maybe X is prey and Y is predator, or they're two prey competing for the same resources. And then the change in the Y population also depends on the relative states of the two populations. And maybe they both start out at time 0 at their respective values. One way we can use to solve the system is with Laplace. We'll see later in the last 2 weeks that you can solve it using matrix methods, and we'll go over those when the time comes. But if you know even some basic stuff about matrices, you'll be good to go there. But Laplace works as well. So let's see how this might work. Here's our linear system. It's a system because it's more than one equation. And let's see what we get. I'm going to jump to a new page. Now, simply, like we do with any of our differential equations where we're going to use Laplace, we just apply Laplace to all sides. So imagine we do that. Imagine we apply Laplace transform to both sides of this. So first take this one and apply Laplace. So we maybe have x prime is equal to ax plus bt. Or why did I say bt? By. Sorry, let me change that. I don't know why I was saying t. So it should depend on x and y. There we go. Actually, if it was t, that would work fine as well. But here I want to use this example. But yeah, if it was t, that actually would have been okay. And we can look at that if you're curious. But for now, we have x prime is equal to ax plus by. And apply Laplace to both sides. Because Laplace is linear, what we can do is on the right-hand side, rewrite it so that we have a Laplace of x plus b Laplace of y. So that's just using linearity. Then on the left-hand side, we'll just use what is the Laplace of a derivative. And what we get in that case is s Laplace of x minus x of 0. And that's just by definition Laplace of a derivative. Okay, well, that seems fine. We can maybe simplify it a little bit. And if we do that, I think we're going to get something like s minus a of Laplace of x is equal to b Laplace of y. And if you wanted to even more, you could simplify it, just because why not? You could simplify it to look like this. And just to go back, if I hadn't corrected this to be by dy and it was bt dt, you would simply have something over here, like a, let's see, t would be 1 over s squared, which is totally okay. That will work. Now, at this point, in some sense, we have one equation and two unknowns, as it were. The unknowns are the Laplace of x and Laplace of y. Previously, we would just have a Laplace of x. Yeah, and someone pointed out I also forgot this guy. Thank you for reminding me. This is x of 0. Yeah, I dropped it up here. So that would be, actually put this plus x naught. Yeah, thank you. Good catch. Yeah, nice. Okay. So at this point, you have two unknowns. You have a Laplace of x and Laplace of y. Usually we would have just Laplace of x, and then we would put everything in terms of s on one side. We would try to get something that looked like this. Laplace of x is equal to some function of s. Then you do algebraic manipulation, take the inverse Laplace transform. But here we have two things. We have Laplace of x and Laplace of y. But notice this was all based on doing it for this first equation, doing the application of Laplace. So we came up with this. This is good. But now we want another one that looks similar. That is another equation. So from this one here, we generated this equation. Now we want to generate another one. So I'm going to copy the first part of this to the next page. From there, we came up with this equation. So I'll copy that. And maybe I'll even put it over here. So we have s minus a Laplace of x. Then we have minus b Laplace of y is equal to x naught. All right, that's what we came up with there. Now we can do something very similar with the second equation. We can take y prime is equal to cx plus dy, apply Laplace to both sides. That's Laplace of cx plus dy. We can use linearity to write c Laplace of x plus d Laplace of y. That's good. And then we have over here s Laplace of y minus y of 0. I got to make sure not to forget this y of 0 again. On the, let's see, on the right-hand side, we can move things over so that we have s minus d Laplace of y. That would be equal to, let's say, c Laplace of x plus y naught. And then if we move that over, we get negative c Laplace of x plus s minus d Laplace of y is equal to y naught. So this would be, let's say, our second equation. For each equation we had in the system, we came up with another equation here. And what we're trying to do is find what is Laplace of x and what is Laplace of y. So now we have these two things. And hopefully I've set it up so it's kind of lined up the right way. That what we notice is there being Laplace of x here and then Laplace of y here. if you think back to instances where you had something like 2c1 plus 3c2 is equal to 4, and then you had like 5c1 minus 2c2 is equal to 3. This is a similar type situation where what you did is you would line these up if you did elimination, and then you would multiply maybe one of the equations by a number, add it to the other equation, and then try to cancel them out. That would be the elimination technique, so that you're just left with one variable. We're going to do the same thing here. So what we did solving for parameters, or what you likely did solving for parameters, it's going to be identical in this case. I'm going to take the system, I'm going to move it over to another page, and then we will look at how to run through this process. Okay, so let's say we want to try to isolate Laplace of x, for instance. And quickly, we'll switch to an actual computational example, just because, this is in most generality and it's getting a little messy, or will be a little messy. If we want to cancel out and just isolate L of x, so we want to cancel out L of y, we want to think about what expression that would take. Well, let's see. Here is s minus d. Here I have negative b. What we would like to do is to take yellow, this equation, multiply all the terms by some given value. So let's give each of these some room. We'll multiply each of the terms by a certain value. I'm going to claim we should multiply by negative, actually that'll be fine, s minus d divided by b, assuming b is not 0. Then we're going to take s minus d divided by b. Then we're going to take s minus d divided by b. The reason for doing that is now we can write s minus d, s minus a over b. And I think you'll see maybe why we want to switch to something more specific shortly. And then we'll get negative s minus d Laplace of y equal to s minus, this should be over b, s minus d over b x naught. Now, the whole reason we did this multiplying by the magenta is so that you can take and add this here. And hopefully I've lined it up right. So now if we take and we add column by column, or, like terms as it were, this part will give us 0, which is what I claim what we want. And then we add these two terms up, then we add these up. And if you do that, what you'll get out is nothing here. You'll get out 0. And so on and so forth. It'll get kind of messy, but you'll ultimately end up with s minus d, s minus a over b, all minus c, that times Laplace of x. That's going to be equal to, on the right-hand side, we're going to have y naught plus s minus d over b times x naught. So it's messy doing it in the most general sense. But if we look at a specific example shortly, I think it'll be maybe a little more manageable because we got just a lot of variables floating around here. So let's look at a specific example. So jumping to that, say we have this linear system here. We're going to apply that same method where we'll think of this as the equation we use to generate an equation using Laplace. And then the same thing here. The first one, take Laplace of x prime, Laplace of 3x plus 5y. Where did I come up with that? That's just yellow here. Then, if we go through that process, we will get 3 Laplace of x plus 5 Laplace of y. And then here we'll have s Laplace of x minus x naught. Do the rearranging, and I think what we'll end up with is s minus 3 Laplace of x minus 5 Laplace of y. That's equal to x naught, which is 1. So just do the little bit of algebra, and I think we'll end up here. So from this first equation, what we ended up with is s minus 3 Laplace of x plus negative 5 Laplace of y is equal to 1. Oh, someone asked, one of the functions is dy. Yeah, I think this did not look very much like dy, but indeed it is. Yep. Now we do the same thing for the second equation. Just to keep this work, I'm going to move this to another page in case we want to refer back to it. So if we have y prime and then 3x plus y, and we apply Laplace to both sides, we'll get something pretty similar to what we just saw. We'll have s Laplace of y minus y of 0 is 3 Laplace of x plus Laplace of y. A little bit of rearranging gives us that we have negative 3 Laplace of x plus s minus 1 Laplace of y is equal to 2, which we'll now put up here. And then now at this point, what we're trying to do again is solve for Laplace of x and or Laplace of y. Maybe I'll let Laplace of x be green here, and I'll let Laplace of y be, let's say, magenta. So we go about and just do elimination as we were starting to do in the more general case. Let me, as usual, put this on a new page in case we want to refer back to this work. In order to, let's say, isolate Laplace of x, let's multiply both sides of, I guess it doesn't really matter. We'll multiply both sides of this by a particular thing. So let's take and multiply both sides of that by what? Over s minus 1 times 5 and if we distribute, we're going to get negative 15 divided by s minus 1 Laplace of x plus 5 Laplace of y. That should be equal to 10 over s minus 1. And now what we're going to do is take this one, add it to this one. If we do that, what we end up with, it looks like, is s minus 3 minus 15 s minus 1. That's multiplied by Laplace of x. Then we have nothing for Laplace of y. That's by design. That's what we wanted. We wanted to eliminate it. Then we have 1 plus 10 over s minus 1. At this point, maybe I'll real quick do some algebraic simplifying. If you're wondering about the steps here, just let me know. I just kind of want to get something here so that we can proceed. But if this is confusing, let me know. Say s minus 3, s minus 1, minus 15 all over s minus 1. I think we can multiply by s minus 1. And what we'll end up with is going to look something like this. S plus 9 all divided by, maybe I'll move this over. Is going to be divided by s squared minus 3 minus 1, so minus 4s plus 3 minus 15. So I guess minus 12. If I did that algebra right. Yeah, okay. And this, of course, can simplify to s plus 9 over s minus 6, s plus 2. Okay. Now, just to make sure I didn't kind of lose you through all of the algebraic steps here, would you just say in chat, as far as you understand it, or as far as you can think of it offhand, what should we do now to solve for x? So what's the step at this point? You don't have to tell me what x is, just what would we do to solve for it? There's going to be kind of two general big steps. So I claim at this point, it's just what you've seen before. I only see a few people saying in chat, so either the rest are confused or just zoned out. So what would you think to do? Or if you're not really sure, you can just say, not sure, which is fine. So let me get a read of a room. I'm only seeing 3 people. Now 4. Okay, there's some more. Thank you for your responses. Indeed, the first thing we'd want to do is partial fraction decomposition. And that's because in some sense we have a product here and we want to turn it into a sum. So do partial fraction decomposition and then do inverse Laplace transform. I'm going to take this, move it on to another page. And let's go through that process really quick. So at this point, if we forget all about the fact that we're working with the system, we just have Laplace of x is equal to this thing. Well, you've done this so far. Because we've done everything else, it may seem like it's a different thing, but it's the same as what you've already done. you're just going to try to find the inverse Laplace transform, but in order to do that, we want to rewrite it using partial fraction decomposition. If we do, we're going to get something like a s minus 6 plus b over s plus 2. We'll have to solve for a and b, but I'll forego that just for the moment, just to see how this ends up. And if we then take the inverse Laplace transform, that's saying that x is equal to a, whatever a is, s minus 6, the inverse Laplace transform of that is going to be e to the 6 t. And then we're going to have plus b e to the negative 2t. That again comes from setting up partial fraction decomposition. And then taking the inverse Laplace transform. You'll do the same thing for y. Now, a and b, that's just a little bit of algebra. And again, we've done partial fraction decomposition many, many times. So for now, I'm going to leave this. You can let me know later if you're still not sure how to solve for a and b, but just for the sake of finishing this up, whatever a and b are, we can solve for them using some algebra. We get this. Now, what about y? Y will go through the same process. Flipping back, we've got, let's see. We've got these two things, which I'm going to take and rewrite. So we originally had this set of equations. But then we also came up with this. We said that L of x is equal to this. So at this point, you can either just substitute in L of x or you can do the elimination process again. Either way, doesn't really matter. Maybe what I will do is substitute in L of x. And in that case, I'm going to get negative 3 s plus 9 divided by s minus 6 s plus 2 plus s minus 1 Laplace of y is equal to 2. So notice I just substituted this into the equation. And someone asked, when we multiply both sides of the equation by a common denominator, will Laplace of x go away? You can do it that way. You can choose to multiply one of these by a particular expression so that when you add the modified equation to the other equation, the L of x cancels and you're just left with L of y. You could certainly do that. Just like how we canceled out the L of y to isolate L of x, you could do the same thing, cancel out L of x to get L of y. You could certainly do that. Here, what I've chosen to do is just substitute this in for L of x here, but you could certainly do the elimination again if you wanted. If that addressed your question, but if not, just let me know. But at this point here, we can now isolate L of y. And what we get is something like this. We get s minus 1 L of y is equal to 2 plus, let's see, 3s plus 27. All right, let's just leave it as 3s plus 9, s minus 6, s plus 2. Then from here, what I might do is actually try to simplify a little bit. So we take 2 times s minus 6 S plus 2. At this point, it's all just some algebra. And let's see. If we go through this, we're going to get, I'll go through this process, but if you know the algebra, I think it'll be just not super surprising what's happening. So we get 2 times s squared minus 6 plus 2, which is minus 4. Actually, we already did this particular one. Nine should be 27. Yep, it should be 27, or I should have this. But why not just write it 27? Yep, good catch. Thank you. And now, if we simplify, we're going to get 2s squared minus 8s plus 3s minus 24 plus 27, assuming I've done all the computations right. I could have messed up. Someone caught that I forgot parentheses, and since I forgot the parentheses up here, that should have been 27. We fixed that, but there may be more errors. Assuming I'm doing all these right, and I'm trying to go fast just so that we can see what happens here. And let's see. I am going to move this up. I'm going to really need to leave that, but let's just say we can now, no, I should leave it. Let's put it over here. This is going to be equal to 2s squared minus 5s plus 3 that's s minus 6, s plus 2. And I feel like this might factor up here. Yeah, okay. That's good. It does. We get s minus 6, s plus 2. Alrighty. All of this gave us in the end. And I apologize. I'm trying to keep it all here so you can see what we've been doing, and yet also parse it so we can keep track of what's going on. But we get s minus 1 Laplace of y. That's equal to 2s minus 3 s minus 1 divided by s minus 6 s plus 2. Divide by s minus 1, you get Laplace of y. And that's going to amount to 2s minus 3 s minus 6 s plus 2. And now we're at the same point we were before, where what we're going to do here is partial fraction decomposition. So partial fraction decomposition. And then we're going to apply inverse Laplace. If you do that, you'll be able to solve for y. I'll put this on a new page. In summary, what we ended up with. So I'm going to just corral all the work we've done here. We had this. Just to summarize, so we don't get too lost in all the computation. So we started with this system. So I'm just going through, I'm going to put everything on one page as a summary if you're wondering why I'm flipping back and forth between everything. We had this. And I should write these two. All right, the summary. We started with this thing. This was just a system of linear differential equations. That was the first thing we did. The second thing, well, the first thing we did was just look at the linear system. The second thing was to go through and find these equations by applying Laplace. Step 2 was apply Laplace. We then do elimination to come up with this L of x and L of y. And then finally, the fourth thing is to do inverse Laplace. And that gave us that x is equal to sum a e to the 6t plus b e to the negative 2t. And then if we did the same thing over here, we'd get y is equal to some, let's say, c e to the 6t minus or plus d e to the negative 2t. Okay, with that, that's our time. Welcome to stick around if you've got questions. Otherwise, we will talk to you later. Have a good weekend. To view the next video in this series, click the link on the right. To view the last video in this series, click the link on the left. If you want to learn more about me, the nerd who's making these videos, visit the website below. And as always, have a good day.